Hello. So in this video, I'm going to explain the difference between vector and raster data. These are the two most common data types that are used in GIS. They are used to display the information we want to see, and it's important to know the difference between them. So I'll begin by first discussing vector data. Vector data is fairly straightforward. It's made up of three key types of data: points, lines, and polygons. I'm going to use central London as my example, as I have ready access to vector data for this area. Points are simply points on a map, so they're XY coordinates. So on our map, I'll display railway stations in central London as points. It doesn't make much sense yet, as you can see. Points can be connected to form lines, and lines will often represent features that are linear in nature, so roads, pipelines, and railways. I have a few lines on my map here that represent railways, roads, and the tidal boundary of the river. So as you can see, our map is beginning to take shape now. It's becoming recognizable. And then, of course, lines can be joined up to create closed shapes, known as polygons. And polygons will depict things that have an area. For example, here we have building footprints, areas of woodland, surface water, so things like ponds, and then we have the river itself. And now we see something that looks a little bit like a map. As you can tell, vector data displays discrete objects. You can select individual points, lines, and polygons. Vector data like this is regarded as intelligent data. This is because it not only displays our data nicely on the screen, but it also allows us to give attributes to each of our points, lines, and polygons. So for example, if I open the attribute table for the train stations, I'll just dock this into our mapping screen. We can see here that each row within this table relates to a feature on our screen. We can also see that there's multiple columns that represent different things, unique identifiers, and there's one that shows us a list of the station names. This allows me to select a row and I can go to that specific station. It's intelligent data. We can see that different features become selected within our GIS layer. This demonstrates how vector data displays discrete objects, so houses, buildings, and roads, individual features. And you can edit those individual objects by editing their attributes. So I could change the location of a point, for example, or the name of one of our stations if I wanted to. All vector data, so points, lines, and polygons, will have attributes that vary in depth and complexity, depending on who made it, and they contain all kinds of information, both text and numeric values. So let me just zoom back to central London and find it. One of the advantages of vector data is that you can switch features off if you think your map is too cluttered. So here, for example, I can remove all the roads, or all the buildings, or all the railway stations. Another key benefit of vector data is that because it's made up of points connected by lines, we can zoom in on our vector data and it won't lose resolution. In other words, it won't break down as you zoom in. It will stay looking sharp on our computer screen. The lines don't get blurred, it stays usable as you zoom in. So that's vector data. The other type of data is raster data, which is a little more complicated. Satellite images, aerial photographs, scanned maps, and elevation models. These are all types of raster-based data, and they come in a variety of file types. So bitmaps, JPEGs, and TIFF files are to name just a few. So if I switch off our points, lines, and polygons, that is our vector data, I'll open up a raster I have of the same area. In the simplest terms, and as you can see, you can think of raster data as an image, a digital image. And like with any digital image, as you zoom in, you'll realize that it's made up of an evenly spaced grid of pixels, or cells. And these are divided into rows and columns. Each pixel is assigned data, that is values, and together they make up the image. And this allows us to effectively gain full coverage of an area, unlike vector data, where there were gaps of nothing between our objects. However, also, not like vector data, this means that when we zoom in on a raster, the sharp resolution of the image is lost. It becomes blurry and the pixels get bigger. So while vector data looks clear no matter what our zoom level, raster data is designed to work at more specific zoom levels. So they are good as base maps, backdrops, and for context. But they'll degrade as we zoom in, like with any digital image. The important thing to remember is that for a raster, the world is divided into these evenly spaced pixels, or cells, and each cell is assigned values, such as elevation, or temperature, or color. This means rasters are typically used to represent continuous data, so entire areas. So let's have a look at a few different examples. As I said, rasters are often used as base maps, that is, for context. Here I have a colour image. It's an Ordnance Survey map of central London. Because it's a colour map, we can assume that the values that are held within each pixel relates to a colour within the human visual spectrum. Colour images, like these, are what are referred to as multi-band rasters. That is, the raster contains multiple values. Any colour image is a multi-band raster. For this image, each pixel will, by default, contain the values for red, green, or blue. These are the primary colours, the three colours of light we can see, and which our computer uses to display the colours of the raster image. To explain how this works then, if I click on the properties of the raster here, we can see it is made up of many different values, hundreds in fact. Each pixel within our image has been assigned one of these values. On the left, we can see that each value, each number, is assigned a colour from within the red, green, blue spectrum, our visual spectrum, and together they make up the image we can see. So if I zoom in here and click on a pixel, it should give us the value that's been assigned to that specific pixel. So I'll zoom in on the river here and click on one of these blue pixels. I can see that it gives me its value here. If I then go into the properties and search for that value, it shows me the colour that's been assigned to that pixel. That's essentially how a raster works. But those values don't have to relate to colour. They can relate to other things too, like temperature or elevation. So let's have a look at another raster example. Here is a digital elevation model, which is a raster. Unlike the colour image, with each value being associated with a colour, for the DTM, each cell's value is a height. The darker areas here represent areas of low elevation, like the floor of a valley or a river, while the lighter shades represent higher elevations. So here we have mountains. If we go into the properties, we can see that this is a single band raster. The cells only hold one set of data, elevation values. The min and max values here represent the height spectrum of the area in meters. Each pixel within our elevation model has been assigned a height that will fall somewhere between these two values. So it's essentially telling us that nothing in this image is lower than 20 meters below sea level or higher than 1347 meters above sea level. This tab here, color gradient, is telling us that the lower end of the spectrum will be displayed in black, whereas the higher end will be displayed in white. This will allow us to see the elevation, as it were. So if I come out of Properties and I right-click on some of the lighter areas, it should give us the height above sea level for that particular pixel. And as it's light, it should be on the higher end of the height spectrum. And then, if we select a pixel within the darker areas, it should give us a much lower value. This demonstrates nicely how rasters are continuous data. So as you can see, it covers a whole area rather than just being discrete units, like individual buildings or streets, like vector data does. But we can, of course, depict things like elevation as vector data. For instance, here, we have a vector shapefile that depicts contour lines for the same area. If we click on one of those, so if I go into one of these mountains here, if I click on one of these, it tells us that that line represents 660 meters above sea level. That entire line represents that mark on the landscape. And they go up or down in 5-meter increments. So that one is 665 meters above sea level. But whereas the raster gave us continuous data across the entire area, the vector lines won't give us the heights in between those values, the heights between those lines. Elevation isn't the only type of continuous data that we have, of course. It could be anything. Pollution levels, areas of deprivation, flood alert areas. There's all kinds of data that can be represented using raster layers if we want to show something as continuous. That is, as a surface across an area. So that's elevation raster data. So let's have a look at one more example. I'll just close this. Another type is a Boolean raster. So let's say that I want to know what is observable from this point on this mountain. On our elevation model, I've run what is called a viewshed analysis on this point. And this has created a very basic raster image that shows us what can and what can't be seen from that point. You can see that this raster is made up of pixels that only have one of two values, either 0 or 1. Essentially, it's a true or false image. 1 means true and 0 means false. So all those pixels which represent an area which cannot be seen from my observable point on the mountain, they've been given a value of 0. That is false. And that is depicted in black. If it can be seen from my point, it has been given a value of 1. So that is true, and those pixels are white. So there are a few examples of the different types of raster and vector data, and I hope that clarifies the difference between the two.